Yeah, first of all, thank you for inviting me to this good opportunity to express my recent work about kinetic theory. And can you see it? Yes. So today I will talk about the main topic is a kinetic theory, but we are talking about the curved spacetime effect or background gravitational effect on kinetic theory, especially in the fermionic system. So before going to the detail of my research topic, so let us briefly review the background of my interest. So now we can create the extreme environment like the age just after Big Bang. In this stage, in our universe, we have the hot matter, so-called cold plasma. On the other hand, in our environment, so we don't have such a hot matter. Instead of that, we have the hadrons, which constructs our anything around around us. So if you use the heavy ion collision, so-called heavy ion collision experiment, then we can collide the hadrons with very high speed, like a speed of light. Then we can create the hot matter, cold plasma on the Earth. So this is the heavy ion collision experiment. And recently, we got a very big news about the heavy ion collision experiment. So a few years ago, we can generate and observe very huge vorticity in the cold plasma, which scale is 10 to the 21 Hertz. And this is very large, as you can see, as you compare with the rotation angular velocity of the Earth, or the tornado, or pulsar, or superfluid helium. And actually, this achievement is reported in the Nature with and in that Nature has reported this big news with the cover of the cover with this large velocity, that large vorticity. And so in our community recently, the rotation is a very important and interesting topic. So in this sense, we need to investigate more about the quark matter and the rotational effect. And one of the interesting physics and the rotation, or interesting physics of the rotating quark matter, is the so-called chiral vertical effect. So this effect is explained as follows. So if you have some cork matter, and then you rotate this matter like this. Then we can observe the current along this direction. So along the rotational axis. So of course, in the classical level, we cannot expect such a transport effect. However, due to the quantum anomaly in Dirac theory, this such an unusual current is generated. And here, this transport coefficient can be completely determined by the theory, in particular, the anomaly in the theory. And originally, such a unusual transport phenomena is just a topic of the matter in the matter existing in the early universe, namely the cork-gluon plasma. However, recent achievement of other Dirac matter like Dirac same metal or wire same metal, and also we know that the chiral matter exists in our universe, such as a neutrino, which is a massless fermion. Namely, this unusual topological transport is a topic which is a universal property of the chiral matter. So in that sense, the study of the chiral transport phenomena is very important topic of the modern quantum physics. So now, we are going to talk about the general concept of the transport phenomena. So transport phenomena is induced by some external force acting on the particle. So for example, if this particle feels the external force aligned in this direction, we have some current along this direction. So this is a general concept of the transport phenomena. For example, if you have charged particle, and if you apply in the electric field along this direction, then these particle feels a force along this direction, and they move along this direction. And eventually, we get the current along this direction. And similarly, this is not just similarly, when you have a temperature gradient along this direction, then also we get the current along this direction, because if you have the temperature gradient like this, so in this box, we have high temperature gas on the left-hand side, and the right side is a low temperature gas. Then the difference of the kinetic energy of this particle, this partition is moved to push to this direction. And this is effective force along this direction. So in that sense, And the temperature gradient is very similar to the electric field. And eventually we get a current like this. And actually, these currents are known as Ohm's law or the Fourier's law under the electric field or temperature gradient. And for these phenomena, we get the electric current or energy current. So this is just a classical physics. On the other hand, if you put a magnetic field or rotation, we cannot get transport phenomena in the classical level, because even if you put the magnetic field for charged particle, the particle just moves along this direction. Namely, we don't have the transverse motion, longitudinal motion of the charged particle. Similarly, the rotation cannot generate a longitudinal force like this. In that sense, they cannot generate some transport phenomena. However, if you go to the quantum theory, the situation should change. So first, if you put the magnetic field for charged particle, due to the magnetization coupling, the particle spin along this direction. And similarly, spin vorticity coupling align the spin to this direction. And furthermore, if you consider the chiral fermion or massless fermion, massless particle, then momentum direction should be parallel or antiparallel to the spin direction. Now we are considering the right-handed chiral fermion. Then momentum direction should be along this direction. And also, the rotating fermion has a momentum like this. Then, this situation implies that we can generate some transport phenomena along direction of B or omega. And this is actually very naive explanation of the chiral magnetic effect or chiral vortical effect. So this phenomena is a magnetic counterpart of the chiral vortical effect. So this very naive argument tells us that if the spin coupled to some external field, then we can get something special. Then let us look for other external field coupled with the spin. So one example is gravity, which is actually a main topic of our work. And before going to the quantum theory, first let us start from the thinking experiment of classical physics. So first we prepare some spinning particle where the spin is described by the spin tensor S mu nu. So now I write the the Earth here as a classical spinning particle. And also, we prepared some curved background geometry like this. And the gravitational effect of this geometry is described by the Riemann tensor like this. Then the question is, what is the trajectory of this spinning particle on curved geometry? Actually, the answer is has found a very long time ago. And the answer can be found from the so-called MPD equation. So this is the equation of motion for the spinning particle. The P is the momentum of this particle. The important point is that we have some correction term, which is proportional to S and R. And this is called the spin Riemann curvature coupling. And I want to emphasize again, this is just classical physics. However, from this sort of experiment, we can expect that the chiral fermion can be coupled with the Riemann tensor, and the chiral fermion can be affected by the curved geometry effect. So this is one of the motivation of our work, and I want to, I will show that actually chiral fermion can be affected by the Riemann curvature. And another motivation of our work is as follows. So if you get the kinetic theory under the gravitational effect, then we can discuss the genuine gravitational effect for some quantum particle, like neutrino or photon or electron in our universe. And also we can extend this discussion to the torsional geometry. Indeed, in condensed matter physics, some people discuss the torsional effect in the condensed matter. And then we can expect our formulation can be applied to such a torsional material. And finally, fluid motion, I want to emphasize that fluid motion is can be regarded as some geometrical effect. For example, if you have some vertical profile in the background fluid like this, and temperature dependence like this, then this situation can be described by the geometry with non-vanishing the rich tensor R0I or Rij. So in this sense, the kinetic theory under the gravitational effect can be applied to the usual kinetic theory under the fluid motion, background fluid motion. And this means that our new formulation can be applied heavy ion collision experiment with strong vorticity or condensed matter physics with the fluid of the Dirac fermions. Okay, and then one of the most promising theoretical tool of the transport phenomena is so-called chiral kinetic theory. And this is just the Boltzmann transport theory involving the chirality of the fermion. For example, so this is a classical part of the Boltzmann transport theory, but if you go to the semi-classical theory, we need to involve some quantum correction part like this. And so the main goal of this talk is to explain that how we can generalize the chiral kinetic theory in the curved space-time. And the second goal is based on this new formalism, I want to derive the new transport phenomena induced by the gravity. This is a first part and introduction of my talk. And can I proceed with my talk? Okay. So before going to the curved space case, first I want to review the basic concept of the chiral kinetic theory. So there are several derivations of the this kinetic theory. But the easiest way is as follows. Easiest way is a path integral derivation. So now we start from the one particle effective action. And here, this is just a classical action, one particular action under the external electromagnetic field. And here, x is a coordinate of the particle and p is a momentum. And a is a gauge field. And from this action, you can easily derive the equation of motion for this particle. And then we get a Lorentz force like this, and the velocity is given this form. And the kinetic equation of this system is described by this form. This is just a usual Boltzmann equation. And also we can calculate the current from this theory. And the current is defined by this form. The velocity times distribution function f. So integral of this product. This is the current. And of course, this is because this is the classical theory. The conservation law should hold like this. The divergence of J should vanish. So this is a classical kinetic theory. And if you go to the semi-classical theory, we have some similar quantum correction in the theory. So first of all, we have some new term proportional to A. And here h bar is a Planck constant, and A is Berry phase. And also the dispersion relation, energy dispersion is modified like this. And this second term is nothing but the magnetization coupling of the fermion. In a similar manner, from this effective action, we can derive the equation of motion for this particle. And we get some new part like this p dot cross omega. And omega is defined by this one. And namely, this omega corresponds to the Berry curvature. So very roughly speaking, if you go to the semi-classical theory, we get the new term proportional to the Berry curvature. And this term, okay, and also the current should be modified like this. On the top of the usual current, we have some extra term like this. And the first one corresponds to the anomalous Fourier effect, which is given by electric field cross Berry curvature. And the second term corresponds to the chiral magnetic current. And the third term corresponds to the magnetization current. So because this omega is given by this form, and now we are talking about the chiral fermionic case. So the momentum direction is the same as the spin direction. And namely, this omega times f is a, roughly speaking, this is the total amount of the spin or magnetization. And if you move out this nabla, and then we get the nabla cross and like this. So this is a magnetization current. And other important point is due to the anomaly, the divergence is non-vanishing. So due to the anomaly, we have anomaly term on the right-hand side of the divergence of J. So far, we are talking about roughly talking about the basic concept of the kinetic theory, the chiral kinetic theory. The most important point is that Lorentz covariance of the theory. So now we start from the situation where the two particles collide from this direction and this direction. And they go out to this direction and this direction. So in this case, we have the momentum P in incoming particle. This is the same momentum P in, but the direction are opposite. And then after the collision, we have the P out and the P out like this. Okay, now we have to check the angular momentum conservation. So delta L and the delta S means difference of the orbital angular momentum and the spin angular momentum. difference between the before collision and after the collision. So first, from these two momentum, it is obvious that we have no net angular orbital angular momentum. And also, after the collision, we have no orbital angular momentum, which means delta L should be 0. And similarly, there, the chiral fermion, which has the spin aligned with the particle momentum, this S, the sum of these two vectors, we found that the total spin is 0. And also, even after the collision, the net spin angular momentum is 0. So namely, the delta S should be 0. So actually, this is the observation at the center of the mass. So now I want to take some Lorentz boost. Okay, now we take the boost in this direction. And then the situation is slightly changing. So before the collision, they have the different momentum. And due to the difference of the incoming momentum, the outgoing momentum aligned tilted, slightly tilted like this. And then we found that although the net momentum, orbital momentum is still 0, even before or even after the collision, but the spin alignment is slightly changing. So before the collision, we have no net spin, spin angular momentum. However, after the collision, we have finite spin angular momentum along this direction. So this means that this collision breaks the angular momentum conservation. Because in this case, we respect the angular momentum conservation, total angular momentum conservation. But in this case, we generate the finite difference of the total angular momentum. This means such a usual boost is actually incorrect. And then we need to consider the modified boost situation like this. So correct situation is like this. So first we collide two particles, and incoming particles the same as above one. However, after the collision, the particle should be shifted along this direction, namely the shifted on the plane, collisional plane, because as I said, as I said, due to the Lorentz boost, we have the finite difference of the spin angular momentum. So to keep the total angular momentum conservation, we need finite difference of the orbital part. So in order to get this finite contribution from the orbital part, we need some shift of the position of the particle. So desired situation is this one. So this is a very special property of the chiral kinetic theory. And the important point is that, of course, the total angular momentum conservation should be respected in any frame. However, if you go to the different frame, the total angular momentum should be frame dependently decomposed. For example, the first frame, we have no net orbital angular momentum and no net spin angular momentum. But after the modified boost, we have finite quantities like this. So this means that the total angular momentum J is frame dependently decomposed. And also, I want to emphasize that the distribution function f itself is not Lorentz scalar, because if you change the frame, then definition of the P is changed. So eventually, the form of f is changed if you take the Lorentz boost. So f itself is not Lorentz scale. So now this is a very naive argument of the Lorentz covariance of the chiral kinetic theory. However, we have an alternative manner to explain the Lorentz covariance of the chiral kinetic theory. And this alternative manner is more straightforward than this explanation. So this is nothing but the method from the quantum field theory. So now we are going to talk about the kinetic theory derived from the quantum field theory. So first, I want to explain how to describe the kinetic theory from the quantum field theory. So first, we prepare the many-body system in some box like this. And I want to talk about the two different cases. The first one is the classical regime. So this blue circle is the particle of the system. And this L is a difference of these particles. And also, we have another scale of this system, which is lambda. So this lambda describes the size of the wave function. If this lambda is much smaller than L, then we can apply the classical theory to describe the dynamics of the system. So in that case, the particle distribution can be expressed by one function, like distribution function n here. And from this distribution function, we can evaluate some observable like current or energy momentum tensor, like this form. So this is the first situation. And another situation is this one. So semi-classical regime. If lambda is not much smaller than the L, or lambda is very, so in this regime, the wave function can be overlapped, or there are interference of the different wave functions. So then we need to take into account the quantum correction of the particles. So in this case, particle distribution, it cannot be described by the usual distribution function. Instead of that, we need consider the Green's function, or more precisely, we need use the Wigner function of this Green's function. And for latter convenience, I introduced the different function R, calligraphic R. And this is just a projection of the Wigner function. So this is just a right-handed component of the above Green's function. And by using this Wigner function, W or R mu, we can evaluate the observable like J over T mu like this. So this is actually, so in the following part, we calculate this quantity. And the important point is that the semi-classical approximation is just nothing but the perturbation with respect to lambda. As I said before, this lambda is describes the size of the wave function. And due to the Dobroi relation, this lambda is the same as h bar over p momentum. And from the this expression, so y is appearing here. And the y is a conjugated quantity of the p, which means this scale is the same as y. So hereafter, in order to get the semi-classical theory, we use the perturbation with respect to this quantity y, or h bar over p. So actually, so I used the very long time, and maybe this seminar is 45 minutes. Is it right, Eda?
I think we have time. You can continue 10 minutes, maybe.
Okay.
What do you think, Mathieu and Ayman?
Yeah, 1 hour is correct.
Okay.
I go.
Okay. Fine. Thank you.
Mhm.
I want to skip the detail of the derivation. Okay, then I want to proceed with my talk from the first order general solution. So to get this solution, we need the expansion, as I said before, and we can solve the equation of motion for the Wigner function. Then we get this general solution. And the important point is that so there are three important points. The first one is n, the meaning of n. So here we introduce some quantity n through the spin tensor, this one. And this quantity is nothing but the spin of the particle. So for example, if you choose this unit vector, then we can construct a three-component spin vector. And this is just p hat half. The half means the magnitude of the spin, and p hat is just the direction of the momentum. Namely, so this is the direction of the spin. And also, this n is nothing but the freedom or degrees of freedom of the Lorentz frame. So as I said before, the chiral kinetic theory itself is, the distribution function f is not a Lorentz scalar. And reflecting this fact, f is dependent, f has an n dependence, and n is the n is so-called frame choosing vector. And I want to emphasize this quantity j, or the Wigner function R mu, should be n dependent because they are related physical quantity. So the physical observable should be frame independent. And finally, from this solution, we get the kinetic equation like this one. So these are some special covariant derivative involving the Christoffel symbol. And from this kinetic equation, we can explicitly write down the equation of motion with respect to the p and x. And finally, we can reproduce the MPD equation up to this replacement. So in the early part of my talk, I was talking about the MPD equation in the classical theory. So in this case, we are talking about semi-classical kinetic theory of the chiral fermion. So namely, we reproduce MPD equation from the quantum field theory. And by using this framework, we can evaluate some physical quantity. So one of a good example is the current in the rotating coordinate. So by choosing the rotating coordinate like this. So this is the metric tensor for the registry rotating coordinate. And by definition, from the Wigner function R mu, we can evaluate the particle current J mu. And then we can get the particle current like this one. So here we are choosing the two different frame vector. But the important point is first, for both frame vector n, we get the same expression of the current. So this is correctly reproduced chiral vertical effect. And the difference of these as follows. So for first one, to get the chiral vertical current, we have two different contributions. The first one is the spin part. The spin part is okay, spin part, and the second one is orbital one. However, for the second choice of the frame, we have only one term, and this corresponds to the orbital motion of the rotating particle, because this part is nothing but the Coriolis force in the rotating coordinate. So Coriolis force corresponds to the rotating motion and the orbital motion of the particle. So namely, these two evaluations of the chiral vertical effect express that the total angular momentum J is differently decomposed frame dependently. So I will talk the several slides. Can I proceed with my talk?
Yes, okay.
Yeah, thank you.
Time.
And similarly, we can solve the second order kinetic theory. So second order kinetic theory means, so up to here, we are considering just the first order correction of the H bar, like this one. But if you go to the second order theory, we need to take into account the H bar square contribution. And then, due to the dimension of the Riemann curvatures, if you go to the second order theory, all observables are affected by the Riemann curvature. In other words, if you want to look for the Riemann curvature effect, you need to solve the second order kinetic theory. And although I don't express the explicit form of the second order solution, by using that, we evaluate the observable like this J. This is a current, same as before, and this is energy current. This is a T I0 component of energy momentum tensor. And also non-vanishing quantity, the final last non-vanishing quantity is Tij, like this. So from this result, we found the following three parts. The first one is they are the transport phenomena even at the equilibrium. Namely, for evaluation of these quantities, we are using the general solution, general Wigner function that satisfy the Boltzmann equation. So in that sense, these transport phenomena are non-vanishing even at equilibrium. This is a very special property, and this is very similar property to the chiral magnetic effect or chiral vortical effect. And another interesting point is that the direction of the energy current and charge current. So this J is a charge current, and this JE epsilon is energy current. So in usual case, as I talk in the very first slide, so transport phenomena is a result of the external force acting on the particle. So if you put the external force Fi for some particle, then particle moves this direction, and eventually the charge and energy or momentum of the particle flow the same direction. However, in this case, so we have opposite sign of the particle and charge current and energy current. So namely, the charge current flows this direction, along this direction, but energy current along this direction. So this is never explained in the within the classical physics. The origin should be the spin vorticity, spin curvature, Riemann curvature coupling, which is nothing but physics of the quantum theory. And from this, these three quantities, so we can apply the actual quantum system under the replacement of the Riemann curvature, Rich tensor, and vorticity, or Rich tensor and temperature gradient. So for example, if you have some special profile of the vorticity, then we can generate the current like this. And also, if you have some special profile of the temperature gradient in some material, then we can create the pressure gradient of the material induced by gravitational effect. So they are very tunable effect by the externally tunable effects by the fluid velocity U or temperature profile T. So in that sense, we can expect that this phenomena is actually observed in realistic material. Okay, this is the end of my talk. So thank you so much for your attention.
Thank you so much for
Thank you very much.
this interesting talk and very good review of chiral kinetic theory. I think we have time for the questions. Is there any question? I think Ayman have some questions, maybe. We generally have questions, but if you don't have, I can ask.
Yeah, go ahead. Maybe I will ask some general question later.
Okay. You show the results. You choose the rotating coordinate frame and rest frame, and your equations of motions. In the rest frame, you have Coriolis force, and you get the chiral vertical effect in the current term. But when you choose the rotating coordinates, you couldn't get the Coriolis force, right?
Yeah.
Okay. And you compensate this situation by choosing rotating coordinate frame to get the chiral vertical effect, I think. Yes, here. Yes.
Yeah. Okay. So now the whole quantity are described as quantity in rotating coordinate first, and this one is the rest frame on the rotating coordinate, right? So now I'm writing the whole quantity as a quantity of a rotating coordinate. So this means that this rest frame means the frame co-moving the coordinate, right?
Mm-hmm. Okay. You are still in the rotating coordinate frame.
Yes.
But it's the co-moving frame.
Yeah, this is a co-moving frame. So then your quantity, all of your quantity is the quantity of the rotating coordinate. Then we can correctly reproduce the Coriolis force here. On the other hand, so what is this frame? So this is actually the opposite direction to the rotating vector. So which means this is a frame this is a rest frame of laboratory frame.
Okay. Mm-hmm.
So this is a, okay. Yeah, this is a coordinate rotation, and this n is like this. So in this sense, if you use this frame vector, then the physics is very similar to the usual chiral kinetics theory in laboratory frame. So in that sense, we can get the chiral vertical effect from the two contributions. The first one is a spin, and the second one is a magnetization part. So this is not the totally same as the usual derivation of the chiral vertical current in a flat spacetime. So this is a difference between these two frame choosing vector.
Okay, thanks. Is there any question?
It's already a bit late, but if you just can say two couple of words about, I'm not sure if I understood with, I'm coming back to the start because I don't know a lot of physics. when you have said that rotation can't be counted in the classical framework, and so we have to move to the quantum framework. So if you can just maybe say some more. I'm not sure if I understood why it's from the thought experiment that you have showed. I'm not sure if I understood why it is not the case that we can count for transportation in using classical tool.
Okay. So when we discuss the quantum physics, we often consider the similarity between the quantum spin and the self-rotation of the classical particle. And sometimes the analogy between them works, but of course, sometimes we cannot use a complete analogy between them. And the first sort of experiment is just a very brief and naive expectation of the existence of spin and Riemann curvature coupling. But actually, so before our work, to my best knowledge, there is no concrete calculation, explicit calculation to derive this equation from the quantum field theory. And in that sense, so we have first derived this equation from the quantum field theory. So is it this answer for your question?
Okay, I will consider it as an answer because, as I said, I don't know a lot of details. So it's if I understood, it's mathematically it's not clear where to put the effect of rotation to have to modelize transportation. This is how I can understand it right now, but yeah, I mean, it's normal that I cannot understand all the details.
So you want to know why I discussed the quantum effect in the rotating coordinate. So is this your question? Sorry, I don't clearly understood what your question is. Can you explain?
Actually, it was just about why it is not possible to count for transportation using classical framework. It's a bit, yeah, in this just in this direction. But I just want to remind you that I don't know a lot of physics because I do mathematics. So
I see. Okay. I see. Maybe I need to use this slide to answer your question. So okay, so for example, if you have the electron gas, they are yeah, precisely speaking, they are quantum object, right?
Okay.
And if they the if the size of the wave function of the electron are very, if you have the overlap of the wave functions of the electron, then you need to consider the quantum effect. And the quantum effect is dominant effect to determine the dynamics of the this system.
And
then,
rotation is something that we can't recover without counting for the quantum effects. So it's I can because what the precise point is when you have said that rotation. If I understood, when we add rotation, we can no longer count for rotation in the effect of transportation. If I understood, like when you started the motivation of the work. So
I see.
But
so
yeah. Don't worry if you cannot provide because I know that the question is a bit not well put. So
if you put the very small rotational effect, and the angular velocity is, if angular velocity is very negligible to other scale quantity like temperature or chemical potential, then the classical description is very valid. However, if you consider some effect, some observable linear to the angular velocity, then you need to take into account the quantum correction.
Okay.
And if you, of course, if you consider more stronger angular velocity omega, then you need more quantum correction.
Okay.
In that sense, so this is this related to the perturbation to the external source.
Okay. Thank you for the answer. I think at least I got some general idea.
Yeah, thank you.
Okay, is there any other questions? If not, we would like to thank you again, Kazuya, for this interesting talk, and thank you for all the participants joining us today.
Yeah, thank you for thank you very much.
Thank you. Thank you again.
Okay, then we will get together 2 weeks later for another seminar, I hope.
Yeah. So in 2 weeks, see you again.
And good night, Kazuya, and have a good day for everyone.
Okay.
Yeah, thank you. Yeah, again for inviting me to give a talk in this seminar.